Welcome everyone to the quantum seminar. We're really lucky today to have, I didn't ask how to pronounce your last name. Maybe I'll have you say your entire name.
That's better. Okay, Efekan Kökçü.
Okay. And so Efekan is a graduate student at North Carolina State, where he's working with Alex Kemper. His work is mostly involved finding creative ways to use quantum computers to study quantum many-body systems. Additionally, he spent several months working at IonQ, working on variational quantum algorithms. He'll be here for the remainder of the day, and we'll also be on Monday. So if you have questions from the talk and they're not fully answered during the question period at the end, feel free to just contact him and arrange to get around. And today he'll be telling us about some of his quantum simulation strategies. Let's welcome Efekan.
Why do we keep changing location? Like,
My fault.
sorry. Does anybody know why we're changing location every week?
Because that room is not available, I presume. The
The room was empty. I was there.
Yeah, the room's empty, but like everything is organized as if it's a class, like everything is in rows and columns and.
Oh,
All right, well, something to worry about later. Let's
right.
let Efekan tell us about
sorry.
it.
Sorry.
It's okay. So I kind of assume that I will be presenting from laptop rather than just
It's probably
because I have the controls here.
exactly
Right.
control.
If it is okay, it's better.
Zoom? Are we doing so?
We're sending it to
You check.
YouTube.
YouTube.
Oh, YouTube. Right.
Okay. I don't know how to check the.
Where's the screen?
Yeah, it's streaming.
We don't do Zoom. We're streaming. Something like that, right?
Yeah.
All right, thanks for the kind introduction. So I'm Efekan Kökçü. I'm from North Carolina State University, and I'll be giving you guys a presentation about quantum simulation of many-body systems, time evolution and response functions, and basically like the quantum simulation of these in quantum computers. And I'm a part of Kemper Lab, and these sources fund me, so I got to put them in the presentation so that I can thank them. Okay, anything happen? All right, click. So this is my lab. Basically, like this is Alexander Kemper, this is my PI, and you guys recognize this is me, and these are the other members of my lab. Most of them are my colleagues. Also co-authors. All of them are my colleagues, and also I'm a little bit excited. Sorry.
And take a big deep breath.
Yes. And these are our collaborators. Like we collaborate with Georgetown. Like Thomas Stickman used to be in our lab. Like he's in Maryland right now, and we collaborate with a lot of people in like Berkeley lab. And today actually is like one of the like the works that I'm going to present is like in collaboration with the Berkeley lab. So yeah. Outline of the talk will be this. There are going to be 4 main points. First of all, I'm going to talk about what is a quantum computer, and to basically give you a well-defined structure of like kind of like a language on like what I'm speaking mostly. And after that, I'm going to talk about like how to simulate spin systems in a quantum computer. And then I'm going to talk about like both of these like papers that I was involved in. One of them is going to be about how to time evolve a system, and one of them is going to be about like how to get the linear response functions of a system by using quantum computer, given that you can do time evolution. So let's just start with what is a quantum computer. So as most of you either know or heard, they use qubits, and qubits are basically physically they're implemented by 2-level systems, and you basically mark one of these levels, like energy levels, as 0 state, and the other as state 1, and you basically restrict your Hilbert space on those, so that you end up having like tiny systems, tiny 2-level systems that can actually carry information. so that you can manipulate them and you can basically process the information on those qubits. So qubits are basically two-level systems, and we use 0 and 1 states as in the notation, just like in a usual computer. The thing about qubits is like if you have one qubit, it can be a linear combination of two states. But if you have, for example, n qubits, it can be a linear combination of any to the power of n possibilities. For example, a 3 qubit can be a linear combination of 0, 0, 0 to 0, 0, 1, 0, 1, 0 to all the way to 1, 1, 1. So it will be basically storing exponentially many information, exponentially much information, compared to the number of qubits that you have. So this is basically, as opposed to bits, this is the gist of quantum computers. They're using qubits allows you to put enormous amount of information in a very small system. And this is the thing that allows you to basically shuffle and process a huge amount of information with a small machine. And that is the thing that will bring out some scalability things. And thanks to this, basically, some of the problems that I listed in the parentheses, such as like Shor's algorithm, Max-Scott, Grover's algorithm, and many-body simulation, are basically are the possible like the problems that the quantum computers will bring exponential speed up. And I will be focusing on the many-body simulation, as you already saw in the title. All right.
Sorry.
Yes.
As an information theorist, I'm obliged to protest bullet points.
Protest noted.
We could discuss after. I don't want to be ready something. The basic point is you can only read out n bits faithfully.
Mhm.
You can only read out n bits of information faithfully from n qubits.
Yes.
Okay.
Yeah.
So
You're
it's debatable. All right.
as an answer, like most of the time you need actually just like small amount of information. This is not to produce an exponential amount of information. It is about like you have something and you expand the information in it, you scramble them, and eventually if you're looking for a small number of information, that is the case. For example, in many-body simulation, you can calculate Green's functions. You don't need an exponential amount of information, like. But okay, I'll talk about these. That are great.
I thought you were gonna complain about the use of both.
I was thinking. I was like, here we go.
They're so violent.
Okay. So, well, I talked about qubits, but like, what do we do in quantum computer when we store information? Well, you need to process it, and the way you process it is you apply quantum gates on your system. Currently, like I think every quantum computer is just built by a universal set of gates that are 1 qubit and 2 qubit gates. And in any hardware, you basically find a 2 qubit gate that is controlled NOT that you see here that looks like a lamp. This one. And you have 1 qubit gates. So like this control NOT, I did not put the definitions of those, but basically a control NOT is like if this qubit is 0, then it doesn't do anything. But if this qubit is 1, then it flips this qubit from 0 to 1 or 1 to 0. And the 1 qubit gates are basically like SU2 rotations. Okay, so it's like a qubit can be considered as a spin. And these like 1 qubit rotations are basically designed that way. Like you can rotate them in whichever way you want. You see RZ, you see RX, like those are basically X and Y axis rotations. So with these, you can also show that like for an n qubit, with this universal set of qubits, you can do any n dimensional n qubit unitaries. So basically you can manipulate the information in the quantum computer in whichever way you want. But one thing to note here is this: quantum computers of today is extremely noisy, because how do you apply these things? You need to send certain pulses to a certain physical implementation of these qubits. And the thing is, these 1 qubit gates take about a nanosecond, and they're like the 2 qubit gates takes about a microsecond of a pulse. So basically, considering the fact that your system actually thermalizes because of the interaction with the environment, you would like to apply these as fast as possible, but control NOT gates takes the most time. So therefore, these lamp-shaped guys are kind of like are both friends and enemies. These allow us this entanglement and just like allow us to store vast amount of information in a small place. but also they are hard to implement, and while implementing them, you actually just like lose some information because the system decoheres. So a main task of quantum computing, like when you're trying to make an efficient circuit, is reduce the number of CNOTs. So I cannot emphasize that enough. So that's why there's this like circuit, and I'm pointing out the CNOTs and everything. So yes.
Maybe you already mentioned this while I was in the wrong place, but are you going to talk about, will you be actually implementing whatever you're proposing on a hardware? Or is this only a theory? Are you?
No, we actually implemented them on hardware. We implemented them on hardware.
Okay, so you're going to help us those results.
Yes, exactly. So that finishes what a quantum computer is. Now let's talk about how to simulate the spin system, like how to actually like put this thing in a quantum computer. Well, I already talked about the fact that like qubits are spins, right? Like you can actually imagine them. Well, that's literally what you do for a spin system. You basically put, okay, my 0 state is a spin up, my 1 state is a spin down, and let's just go for it. You could shuffle it just in case you want to have one to be spin up. That is also fine. But there's also another thing, like I think you all know that like there's something that's called Jordan-Wigner transformation, and thanks to that you can actually implement fermions in this as well, because like fermions are also like a two-level system, right? It either exist or not on a site. So you can actually replace the 0 with an empty state and 1 with a like fermion is there kind of a state, and then after that you can implement fermions as well, so that you can do not only spin but like a many-body fermionic system as well. So after you do that, you still need to implement something on the system. Like only having states doesn't allow you to do things. So what would you like to do with like a spin system or a fermion system? There are things that you can do. For example, you might want to find out what the ground state is or a thermal state is or whatever. Like some specific state that is related to some under some conditions of a given Hamiltonian. You might want to find something like that. Or you might want to have a time evolution of a given state, any state that is coming from left-hand side, and you might want to end up measure something about like a state that is time evolved under some certain Hamiltonian. So in both of these cases, you need to build a unitary that actually evolves a given initial state, like that is practically like in every quantum computer, it all starts from 0, 0, 0, 0 state to generate a state that you would like to basically measure things on. So this is called a unitary synthesis problem. You need to basically generate a U, or either you have a given U and you need to write it in terms of like those 1 and 2 qubit gates, or you're given a Hamiltonian and you need to generate this time evolution circuit from those like 1 and 2 qubit gates. So in both cases, you got to do that, and I'm going to show you a little bit of a recipe about time evolution to give you a little bit of a context. By the way, like for ground state preparation, I'm not going to talk about it much, but like there are certain algorithms like such as VQE, QAOA, and all sorts of these algorithms that are there for you to find ground states that are variational, for example. And when you dig into the like literature, you will find a lot more. If you want more, you can talk to me later. So for time evolution side, I just want to give you a concrete example, such as this Kitaev chain. I want to talk about the notation here. For example, this leftmost thing doesn't mean 23 in Roman. So this thing that you see is like their Pauli matrices, and this is like a 5-spin chain. And these I's are identity matrices. And like in quantum computing, the usual description, like that, the usual language that we use is like X, Y, and Z for Pauli matrices. We kind of like are tired of writing sigmas. It's hard to do in LaTeX as well. So because of that, we kind of like prefer this. So what you see here is like a qubit 0 and qubit 1 has an X spin interaction, and here like a qubit 1 and qubit 2 and are having a Y spin interaction, and etc. Okay, so one thing is like you all know Schrödinger's equation. So U of t is basically e to the minus ith. This is the thing that you need to implement to time evolve. But luckily for us, because otherwise we wouldn't have any funding and we wouldn't survive, these things do not commute, and it is hard to do. Like exponentiating this Hamiltonian is not trivial. So in that case, you cannot simply write it in terms of like exponentials of single poly strings like this. One thing Eric is looking at me is like I forgot I'm about to forget to mention that these little things like e to the single poly strings, we can do it in a quantum computer, but e to the this Hamiltonian is hard to do. It is non-trivial to do. But like these single things you can do in a quantum computer, and if basically you can do them and you can append them right next to each other. So it would be very nice if this non-equal sign was an equal sign, that we could actually like, do that in a quantum computer. Okay. But there's a way to do that in an approximate fashion. So if this t time was a very small thing, then if it was an epsilon, when epsilon is a very small number, you could actually write it in this form with an approximate like error that scales like epsilon squared. So this is called trotterization. At least like this is the trotterization that is used in quantum computer all the time. So you digitize the time steps and you choose your time steps into as very small number, and in that case you can actually write your little time step as something that you can implement in the quantum computer. And in this case, for example, this thing that you see here can be implemented in this form, basically. So like this xx gate that you see is basically, for example, like e to the minus I epsilon a xx that's applied in like 0 and 1. I might have messed up the order. Usually just like the left one is the initial state. So you're actually implementing xx first, but it doesn't matter because you're actually, you know, epsilon square calculation. You can switch the order of these, doesn't really matter. This is first order chart, okay? But one thing you should know is like these gates actually have a parameter in. So like this epsilon a goes for this one, epsilon b goes for this one, and etc. So whenever you see this, I try to mean that there are parameters, but I don't want to put them in the figure because it will make it so crowded. So first, all good? Okay. How would you build a time evolution then? Well, you apply this many more times until you actually like reach the the time evolution that you would like. Basically, you apply t over epsilon many times, and well, this is the recipe to have a quantum circuit for a time evolution of a generic Hamiltonian. Well, there are two things. There are a couple of things that I want to mention. One, this approximation becomes pretty much exact when epsilon is just 0. So if you want to get a better result, you got to get your epsilon small enough. But that means that in order to do a fixed, like for example, like t equals t0, like you choose t equals to be 1 second, for example, and you need to choose epsilon to be very small. That requires you to have a like enormous, gigantic circuit. Like you need to apply a lot of gates. And I already told you that like the quantum computers of today is very noisy. We want to reduce the number of CNOTs and etc. And all of these like XX and YY gates, they contain 2 CNOTs each. So basically this circuit, even though it is like a nice recipe to build, if you don't have fault tolerant quantum computers, you will not be able to go to like small enough epsilon, and you're going to have at least theoretical error in the trotter. If you try to reduce your theoretical error, your noise will increase, and then your like implementation error will increase. So because of that, this is not something doable currently. So basically, when t is large enough, you're gonna go for very small epsilon, and then trotter circuits are not reliable, sadly, at least like for the current hardware. So that motivates us to write this paper. Algebraic compression of quantum circuits for independent motion. And right now I'm going to talk about it. So this is, yes.
Do you mind to go 2 slides back?
Yes.
I guess there's another thing you can do. You can parallelize.
Yeah.
You're gonna comment. All right.
So this slide, I should have modified it. This slide should look like, I think, this one. Here, for example, this is like one trotter step. You're right, like you have key knives. But this is again, just since this is like first order trotter, you can actually like shuffle these in whichever way you want, and the error will be other square. Yes, that will be the more efficient one. You're right about it. And thanks for coming. So this is the like the introduction slide of this thing, the algebraic compression of quantum circuits for evolution. So these are the colleagues that are from Berkeley National Lab, and These are the all related, like both papers and like archive preprints that you might find about this. We also have code available in this GitHub page. So well, this method is a constructive Lie algebra based method. I'm going to talk about what they are, like what I mean with this introduction page in the next slide. And it is scalable because it is constructive. There's no variation elements in this. And what it achieves is like, for example, for a given circuit like this, it actually compresses it down all the way to this. I know like they both look similar, but if you notice that there's this 3 dots here on the left, these can be like, I mean, 10,000, there can be like 10,000 gates like this, but like it basically like shrinks that to a basically fixed step circuit. And here, the XX and YY gates, as you see, like as I told you before, they actually have parameters in it. Like for this case, they actually have 1 parameter in it. So how does it do that? So this is basically the punchline I gave you, but let me talk about how does it do it. And to do that, I'm just gonna make it more mathematically general. And in order to do that, I'm just gonna replace these gates with oval-shaped structures that I call block. So mathematically, the object that I call block is defined as an object that satisfies these 3 relations. So each of the block, as you can see, have an index I that you see here, or like I plus 2, I plus 1, as you can see. And also each of these blocks actually have parameters that I don't put in the figures because I don't want to make it extremely crowded again. So basically, these 2 blocks can be different because they have different parameters. Just like the XX gates here, for example, it can have a like theta equals pi over 2 here, theta equals like, I don't know, 0.51 here, and they can be different. These blocks can also be different. And they're going to be mapped to certain quantum gates in a model specific way. I'm going to give you different mappings, but I'm going to talk about the relations right now. So diffusion means basically if you have 2 blocks right next to each other with the same index, they can be merged down to 1 block. This basically means that the blocks form a group. You can see it that way. And they need to commute if they're far enough. So it is like if a block has an index I and the other has I plus 2 or I plus 3 or I plus 4, they commute with each other. And I mean, this structure can be transformed to this. And then there's this turnover structure that we have that if you have an I, like adjacent ones, then this I plus 1, I plus 1 can be turned to I plus 1, I, and vice versa. And this can be turned to, what I mean is like, I mean, for the given parameters on the left, there exists a set of parameters for the right to, so such that this equality is correct. That's what I try to mean. One thing I want you to remember is that, because I'm going to talk about that in the conclusion slide of this, is that these properties are local. So basically, one needs to check only the neighbor gates to apply these. And for the examples that I gave you, you can actually find the other parameters just directly by calculating from the given parameters. We actually provide the input-output functions of like these angles in the paper. Yes.
What does the I represent, and how are these related to the B groups, you said?
So I will just give the examples, and I think it will be more clear there. Okay. So, but like I can just like give you the I. These I's will actually just like kind of represent the rich set of qubits that these apply to. But the Lie group I will talk about later. Okay. So okay, so like I mean, I give you these relations and blocks satisfy these, but then so what? Like I mean, what I use it for? So what we use it for is like basically, I'm just going to give you like a high level thing that you can do first, like the thing on you see on the left. So first of all, like this structure that you see that is like a slash of blocks, we call it cascade. They're not as beautiful as the cascades that I saw that are nearby, but it's like a cascade of blocks, 1, 2, 3, 4, 5. And let's just see what it does to a block that comes from like right, that is a block with index 2. So this 2 will commit with 4 and 5 because they're far enough. So this commutation will apply, and 2 comes all the way to here. And then you see like there's a 2, 3, 2 kind of structure that is basically the right hand side of this turnover. Then applying this turnover, I can basically bring this 2 down, make it a 3, because this 2, 3, 2 can become a 3, 2, 3, right? So you can imagine that as like this block kind of passed through by changing the coefficients of 2 and 3 and itself. And after that, it becomes a 3 that will end up commuting with 1 because it's far enough. So it will go away from this cascade and become a 3. So basically what a cascade does is like anything comes from right will be pushed down 1 index and it will be down. So what if you have a stack of these cascades, like this triangle that you see on the right? So if you have a cascade like this and that and that and that, this 2 will come and past this cascade become a 3, past this one become a 4, past this one become a 5. But now there's like an exceptional case. Right now, this doesn't actually need to pass this cascade because you can apply fusion rule. Because this 5 and my block that turned to 5, they're just right next to each other. So they can become a 5. And then basically this 2 can be absorbed by this triangle structure by just changing the coefficients of these blocks that are right next to this arrow. All right. So the locality kind of like comes in here. You don't need to change your entire circuit. You only change linear number of those that is proportional to the number of qubits, or like the height of this triangle, basically. And in a way that is okay, the kind of like the thing that makes it slightly efficient. So, and the thing that allows me to compress is like this thing eats any block that comes from right. So basically, you can have a million of those coming from right, you will still have a fixed circuit structure. Like after I map these blocks into circuits.
Question.
Yes.
How much of this depend on the one dimensionality of the qubit array? Seems like it's very just up and down, moving.
Oh, so this is independent from that in a sense because like the communication between qubits is independent of them being one
But
dimensional.
if you have loops or something.
Yeah, or you have a 2D grid, like things are not just,
Snake.
yeah, you
It
have,
won't be
you know,
local.
loops going crazy and.
I think I have a slide that will explain something about that you will like. But in this case, like this is just basically I have some structure that I call block, and that makes the qubit communicate.
But you have this 1D locality structure.
Yeah.
Right, that
That's
as I go up in, 1 and 3 can pass each other.
Yeah.
And if they were arranged in a 2-dimensional grid, there would be not only would 1 interfere with 2, but there would be like 5 that interferes with 1. Right, these are more than one set of neighbors.
Yeah, under certain circumstances that I'm going to show you, actually, so can do this too.
Okay.
So, well, I told you that triangle absorbs everything. Now, this will kind of like correspond to the depth of my circuit, and that will be the time that it takes to run the circuit in, for example, a superconducting qubit device, because you can do parallel things. So in that sense, I can actually just use these rules a little bit more to shrink it down more. So instead of having this triangle, I'm not going to explain how to do this one by one because it will take so long time. You can do this on your own. But you can basically shrink this triangle into something that we ironically call a square that is actually just a rectangle, it's not a square. And you can reduce the depth to depth even more. And this basically means that you can compress any number of blocks into first a triangle and then transform that into a square. And this is basically the structure that we have. And remember, for all this thing to work, you just need to satisfy, like your gates need to satisfy all those 3 rules and only those 3 rules. That's basically it.
So the circuit depth is equal to the number of qubits.
In this case, yeah, proportions. It's either 3n/2. Like it's model dependent, actually. Like I mean, if depending on the model, you might need for n qubits, you might need 2n+1 blocks or n blocks, or n-1. Sorry.
Can you describe the conditions in terms of Hamiltonian?
Yeah.
Like what kind of Hamiltonian? So
Just about.
maybe I guess my feeling of the room is that you are saying you can grammatically compress something,
Yes.
and there's no free lunch. So
Yeah.
this magic,
Mhm.
and we want to know.
I'm just about to talk about that.
Okay,
That's just
great.
a perfect time to ask this question. So the well, I talked about blocks and all, but as like one of the audience said, like not everything is sunshine and rainbows. The examples that we include are Kiteo chain. You remember that this is the one that actually like started everything in our minds. Like this was the thing that we inspired from. But then we found transfer field easing model as an example, and transfer field XY model as our most generic example. For this
These
case.
are all 1D.
Yes, these are all 1D spin chains. And to answer your question, they're all free fermion as well. So like they're free, like when you do Jordan-Wigner, they're free fermion models. And there are a couple of things that I just want to note here. Like blocks don't have to be just 2-qubit gates. They can sometimes be 1-qubit gates. And they only don't carry 1 parameter. So for example, in TFX5 case, they can carry 6 parameters. So those are just things that like block is just a generic structure. But all of these mappings, we prove that like they actually satisfies those 3 simple rules that we showed. And these are the number of SINA and like the 2-qubit X gate scalings. I gave the.
So can you generically show that if you have those rules, you must be free fermions?
No.
Let's go that direction.
So
Can you get a mapping onto fermions just from the rules?
I'm not 1% sure. But in some sense, maybe, but you can actually get copies of free fermions too, because you can actually have a block that is like, I don't know, like an XYZZX kind of a gate, and that act on 5 fermions, 5 qubits, and the other one acting on 5 other qubits. They can still satisfy the same thing. You will probably have copies of free fermions. That is one generalization that I can think of, but we actually are trying to find different models that are not free fermion that satisfy these. But yeah, like we are not successful yet about it. But
So far they are free fermions.
yes, so far the examples that we have found.
So is there any criteria of whether some model will work, some model won't, like is there a way to tell whether you can tell something?
So
Like if just somebody randomly throws you a model, yeah, we'll be able to tell like whether your magic works or not.
that is a good question, and to prove it for TF and like TFX5, it was just the proofs that we had given, but that is not that much of a trivial task. But like basically, it's a good question, and that could be a nice research topic. But currently, like these are the examples that we found only, and but I'm happy to talk about it later.
Okay. And maybe a good one is that the most non-trivial structure you need is this, whatever you call it, passing or something. It's this triangle shape thing, flipping or something.
The
Turnover, yeah. It looks a lot like the Young-Baxter equation. Right?
Exactly, yeah.
So
Yes.
you can play with. Definitely, you get non-free fermion with braiding. So I guess there is the recipe.
Yeah.
I'm not sure how what kind of interesting model he gets.
You already asked the question about periodic boundary conditions, and it's still not clear to me whether your rules can be invoked modulo n for n the number of blocks, or whether that's an obstacle if you're trying to build up these squares.
I'm about to go there actually. So currently, if you want to think about it as a transfer field easing model, like a spin model or transfer field XY model, like this structure, this recipe that I gave you actually is only for open boundary conditions. But if I forget about it, could you remind me again? Okay, good. But currently, as I told you, this recipe is just completely good for 1D free fermions as well. And it doesn't have to be just fermion conserving free fermions. It can be like superconducting as well. So like because TFXY, like TFIM is actually a superconducting free fermion model once you do Jordan-Wigner, for example. Okay. So I'm just going to show you the example that we had in the original paper, which is adiabatic time evolution for adiabatic state preparation for the transfer field easing model with basically 5 qubits. So this is the Hamiltonian. We basically vary our J value. We start with J equals 0 and end up at J equals 1. And when J equals 0, you can prepare the ground state of this thing pretty easily. Like that is basically all zeros, like if H is negative, or all ones with if H is positive, then you can basically provide that. And after that, you slowly change your J to 1, and you should actually get to your ground state. And what we plot here is the magnetization, like the average magnetization of the state that we're at for any time. There's a typo. It should be m of t equals 1 over n sum over expectation value of sigma I z. Sorry about that. But this is the data that we got from IBM Q Brooklyn for about like 2.5 years ago that we ran this thing. I think IBM Q Brooklyn is currently retired. You cannot run anything on this right now, but like this is the data we got. So I just need to talk about the data a little bit because we're comparing it to Trotter. This purple and red one are compressed circuits, and the blue and green ones are the Trotters. We basically use arithmetic step preparation because it requires slow time evolution and long time evolution, basically to flex our muscles. So it's like, so the thing is, like, this Trotter is, I mean, like, we picked 2 different time steps. One is 0.05 and 0.25. For blue one, you need so long, so deep circuits. The IBM didn't allow us to run after this point. So that's why the blue actually like cuts here. Like, you actually like have a certain limitation in the hardware. You cannot use it for hours, for one circuit. So as you can see, like this black dash line behind the red one, like both of our algorithms actually like follow it very nicely. Purple one kind of just fall behind because it is.
Best ones, what does delta T mean? There's no
Delta T is the time
here.
steps.
There's no time step in your investing, is there?
There is.
Oh, there is.
Uh-huh. Yeah.
It's the same number of things, but.
Yes, exactly.
But you could take the limit delta T goes to 0.
So what happens is this, like, we can take delta T goes to 0, but we also would like to compare it to a Trotter. So, like, in order to get a fair comparison, we need to just like put the same delta T. So basically that's why we choose 2 different delta T values. For example, purple doesn't follow the black dashed line exactly because like delta T is slightly big. It's like there's some Trotter error. This is like theoretical error that you're seeing. And
The black dash line is the circle.
it is exact error. This is 5 sides. Like, we basically did a simple matrix calculation by NumPy to generate that. And yeah. And these are actual results from the hardware that we do not use any error mitigation at all. And our circuits use 20 C0s, whereas like for Trotter circuits, in order for you to understand the scale of the circuit, we zoomed into this like black rectangle here. Like the green one actually is like they use this much C0s when T equals 3.5, for example. Like 112 already, and the blue one uses 560 C0s, and that's why you actually like see decoherence in the signal immediately. Okay. Now I'm answering the both the long range hopping question. So it's like, if you have a connection between like the site 1 and site 5, then what happens? In a way, it will answer the periodic boundary condition too, but I'm just gonna have a little bit note about that later. Like, this is called, like, if you're dealing with only 3 fermions. Right now I'm only focusing on 3 fermions, and I'm not talking about like the generic block structure anymore. There's a gate that is called fermionic swap gate that is, in terms of matrices, it's given this way. And you can show that it can be written as the multiplication of these unitaries. This gate directly can be used, like, applied this way. And why do I care about this? This fermionic swap can carry your creation and annihilation operators from one qubit to the other. So if you apply this form, the C1 or C1 dagger can be transformed to C4 and C4 dagger. What does it allow me is, if you have a long range hopping like this, they can be transformed into a nearest neighbor hopping. So you can implement this long range hopping with F swaps and a nearest neighbor hopping. All right. So far so good. But can I compress this fermionic swap? Oh yeah, because this structure that you see here is basically a TFXY block. Like, there's the XX, there's YY, there's an IZ, and there's a ZI, and therefore you can actually like write this fermionic swap operator as a TFXY block as well. So you can basically implement a 3 fermion in any lattice. When you trotterize that Hamiltonian, you can write that trotterized, like, 1 trotter step in terms of TFXY blocks, and you can compress it down to the circuit structure that I'm showing you. So basically, we applied this into a 4x4 type binding model. The structure that you see here on the left, this is like the 4x4 open boundary condition type binding model. We start the model from it's completely homogeneous. Like, that's why I didn't give the Hamiltonian. Like, the hoppings are just square lattice structure. So we put basically 1 particle into site 0, and here you see the like the amplitude to be in Manhattan, this one, and Manhattan, this two, and etc. to the original point. And this on the left hand side, you see the like quantum computer result directly. This is called the quantum processing unit result. And like this is the simulator result. And with the naked eye, you will not be able to see much of a difference. The qualitative behavior matches. The only difference that you're going to recognize is this, like it gets slightly more purpley towards the middle in the quantum processing unit compared to the simulator. The reason is that we're kind of like just summing all over like these qubits, and each qubit has some decoherence noise. When you add them, that actually like accumulates more if you're adding more and more qubits. So these are on average. That's literally just like summed up. That's the reason that you have more error towards the center. And we run this in IBM Q Washington as I write here. And this is the qubit mapping that we have chosen. We need to have a line because yeah, like as you guys already saw that like the circuit structure that I have needs some kind of like nearest neighbor connection, and like that's why we actually like want to have a line in a given hardware. After that, we also tried if we can implement Anderson localization in this 4x4 type binding model by adding a random potential.
For this 4x4 one, how deep was your circuit?
I forgot to put that in the
Or
detail.
how many C naughts, I guess is the crucial question.
I don't exactly remember, but I mean, it was, I think it's order of 50-ish. But we can calculate it after, I think.
Yeah, but
Actually, I can do that, like, because
no, that's close enough.
all right, cool.
Maybe a quick clarification.
Yes.
So this is a single particle. So
Mhm.
it doesn't actually bother us if it's a boson or Fermi. It's just one particle moving around, is that right?
Yes, like in this case, like it is a particle conserving Hamiltonian, it's a single particle. But like this is basically in a way benchmarking our algorithm, and can we actually run it? So that's why model is not too important. We just wanted to have like this ballistic structure. Like we wanted to see this, and like the data was enough. Mhm.
Okay.
Yeah.
Just a minor clarification, why is the distance there just fixed?
This is so it is not 6, I think. I'm not sure.
Yes.
Yeah, it's from diagonal.
It's medium distance.
Yeah, like it is a medium distance. Yeah, it is the yeah, Manhattan distance. Sorry.
Good.
For a second, I thought that it maybe was 5 in tops. Yeah. All right. Good. And we added a random potential to this to actually see if we can implement Anderson localization, and we were able to do this. Once you add a random potential, like you see that like, your particle is actually really stuck here with an error around this break. Like it doesn't exceed this, but this is expected for like we ran this about 2 years ago. Like currently, I think the hardwares are better. And as I told you, this is like the only thing that we have done was I think that the only thing that we have done is when we measured the bit strings, we discarded all the bit strings that doesn't have only one particle. Like we got rid of the 0 particle, 2 particle, 3 particle bit strings and measured it. But we did not do any error mitigation. We did not do any like any other techniques such as like dynamical coupling or any fault tolerant things. We did not do any of those.
And what fraction of the runs ended up having the wrong number of particles?
That is on the paper that I don't know right now.
But was it a rare thing, or was it like 90% of them?
We lost a lot of shots. That's what I know about. Like at least half of them we lost. Like or like I need to refer to the paper for that because that part of it was done by someone else.
How do you guys implement the random potential?
You just choose a random potential, which is some random generator, and that's it. Like it's not time dependent. It's just like position dependent. It's a local potential. That's it. And yeah. So that concludes the compression. And now I gotta talk about the response function paper, and apparently I have 18 minutes left. Yeah. All right.
Okay, sorry.
and it's better to get questions and stuff.
Uh-huh.
I had to do my going back to the previous slides. Actually, this is a good time to ask. So right now, it looks like the connectivity, I can totally arrange it in 1D line, no problem.
Mhm.
But you would have connectivity between 1 and 5, 5 and 9, 9, like, right, like I have a lot of non-local gates if I try to draw the
Yeah.
qubits in an array.
It's this.
So it's like 1 to 5, nothing is at the end of anything, right? And then I have 10 to 11, and then some, 9 to 13. You
Yeah.
always try to move them to the nearest neighbor before you implement it, or what, like, because if I really arrange the qubit
Mhm.
in a 2D grid and I draw all the vertical lines as if it's time, where do I draw the triangle where you try to compress things in?
So the
Or-
thing is, I wish I put the figure from our like the latest paper from this, because this is from that.
Yeah.
But what happens is this: you have a trotter step, and if you have a long range interaction like that, so long range hopping like this, you transform it into an f swap times nearest neighbor hopping, and you undo those f swaps. So in any, like, if you want to hop from this to this, you basically end up having a boomerangish structure like this. But that basically gives you some, I don't know, just like some additional number of blocks that you're going to end up compressing anyway. So the triangle structure is remaining the same. Only the trotter step will have more blocks in it, but it will still eat it and eventually be compressed at the end anyway. So the circuit structure doesn't change.
I see. So the price being paid here is that you basically have to almost physically move the sides close to each other.
Yeah,
and let it hop, and then you bring that guy.
Mhm.
apart. Okay.
Yeah, you can actually like see it that way too.
But in the. I'm hearing different things from the two of you. So you've turned what is a interaction between 1 and 5 into sequentially a gate between 1 and 2, then 2 and 3, then 3 and 4, then 4 and 5,
Mhm.
and then 3 and 4, then 2 and 3, and then 1 and 2.
Mhm.
And then you do your compression thing, which then turns it all into this fixed depth thing.
Yes. So like, as he said, I'm kind of moving one fermion from all the way to here so that I can do a nearest neighbor hopping. But on the other hand, after I generate that structure, like I basically compress all of down by using my algorithm.
Right.
Yeah, that's
And I guess the small quibble is that the circuit, the geometry of the qubit is already 2D.
Oh, yeah.
They're very spread out and bring things back close together and move things back. That sounds like a little bit waste of resource.
Worse than.
that is required for fermions because you need to keep track of Jordan-Wigner. Yeah,
that's
because like 1 to 4 doesn't mean that only 1 and 4 is included. You also need to include like 2 and 3 as well.
Yeah.
Like that's required.
fermions.
For fermionic, yes. If it was a spin model, like if you were trying to do some Kagame like spin model here, yeah, that wouldn't make sense to move things around. You can just directly map it to here, yes. But I understand what you mean. All right.
You're down to about 10 minutes.
All right. It's okay. I think I will be able to zoom through this. So now this is our other paper, basically just like measuring response functions. So it is this, and like these are the co-authors, and you can actually reach to this paper from this archive preprint. So basically, I showed you how to evolve a given state. But what are you going to measure? So like, why did you evolve this, right? As physicists, we like measuring response functions. Why? Because you can actually measure them in the material in experiments. So you can actually have your theory. You can, at the end of the day, you calculate the response functions out of your theory and check if they match to the experiment or not, or you have predictions, you measure it, or you want to run dynamical mean field theory. And in that case, you need to have a Green's function to be measured all the time anyway, to actually obtain convergence. Like there are many reasons that you'd like to measure any kind of response functions, and the response functions are given in this form. So you can measure, you can get a response function in position or momentum or time or frequency basis. And it is completely up to like what you'd like to do. Like you can do pen and paper, or you can do a numerical calculation, and you can choose whichever. So usually like if you stick with the Many-Body textbook, the chi, like this response function that I've shown you is usually Fourier transform into this structure. but we don't know how to invert matrices in pen and paper, so we actually plug in an energy basis here, and we get the lemma representation. So this is the usual form that you see the response functions, and most of the numerical algorithms actually work on this, as far as I know, in the classical computers. And there are also some quantum computing algorithms that actually approaches the calculation of the response functions by using lemma representation. Or you can go back to your roots, and you can actually directly use this because, well, I just have an implementation of e to the minus I0t. I just shown you, I can do that for free fermions, so we can actually use this. So there are also classical algorithms that use these, as far as I know, they're DMRG based, but there are more and more quantum algorithms that actually uses this. So we picked this as a group and to measure response functions, and we're going to be using this form with the time evolution. The most generic algorithm, for example, in time evolution, that is Schroederization, right? For measuring response functions, that is the Hadamard test, the circuit that you see on the left. So basically, if you want to measure an expectation value like this, what you do is you have your 4 system qubits here, and you add just one more qubit that is called an ancillary qubit, and you apply this A operator in a controlled fashion. And this basically means that if this ancillary is 0, don't apply it at all. If ancillary is 1, apply A to your system. And then you evolve your system, and then you apply B in the controlled fashion, and you apply Hadamards, and then eventually you measure your ancillary qubit. And I need you guys to trust me that this expectation value gives this measurement gives you this expectation value basically.
ABA has to be unitary.
Yes, in this case, yes. But for example, if you there's annihilation creation operators, that is x plus iy, and x is a unitary, polys are unitaries anyway. So, but those are good questions. And one thing that I'm going to talk about is this thing requires an ancillary qubit. I want you to remember this, and A and B should be local in the space that we're working in. If we're working in position space, then they better be local in position space. If we're working in momentum, they have to be local in momentum space, because otherwise I need to apply a bunch of these, and you see that they all need to be controlled. They increase the number of CNAs that I need to apply, increase the noise. So these are the things that I want you to remember about the Hadamard test. And there's the R method, which is basically simulating an experiment. You hit something and listen to what kind of sound it makes. That is the usual way to measure response functions. So you hit it with a signal with an operator that is proportional to an operator B, and you evolve it with your Hamiltonian, and then eventually measure the end product. And that measurement will give you, in the end, you will be measuring the operator A. So in the end, you will have an expectation value of A of t, and then you can take a functional derivative of this thing with respect to the signal that you have, that will give you the response function. But one thing that you can look at is this is not just A of A times B, this is A comma B. So this is a commutator response function. That's why we call it bosonic or commutator response function. That thing I just need to remember. So we are not actually calculating AT times B. But one other question can come from here is that how to calculate this functional derivative, because numerical derivation is kind of hard. If your system is time translationally invariant, what we actually do is realizing that the response function is going to be a function of t minus t prime rather than t and t prime. And after that, you do a Fourier transformation, and calculation of response function becomes just a mere division of real numbers rather than numerical derivation. So this is basically what we do. We measure A of t, we Fourier transform it, and we Fourier transform the signal that we hit the system with, and then we take the ratio, and that is the frequency basis representation of our response function. And if you want the time basic representation, you want the Fourier transform. From this, I just want to talk about you don't need to choose your signal to be just like a hammer on one time. It can be actually a long signal. You can you can change its frequency components. It has certain advantages. It can actually make your you can just calculate a response function at a given frequency. If you want to do that only, then you just put a given frequency on your signal, and you can do that. And yeah, this basically, I don't have time to talk about all the advantages of it, but this can provide some error mitigation in quantum computing. Apart from that, we can do momentum selectivity with no additional cost. So remember that I actually talked about, like in the Hadamard test, these operators better be local in position space, because applying all of them together will increase the number of C-naughts. Well, in our method, applying all of them together will only increase the number of 1-qubit gates, not like the 2-qubit gates. So therefore, it's basically at no cost you can do momentum representation directly. And for most of the like the Hamiltonians that we would like to measure the Green's function for, they are translationally invariant, so they conserve momentum. So measuring a Green's function, the momentum basis is better. And I'm just going to show you like why it is better with the noisy and hardware implementation in a second. So I have shown you the bosonic or commutator response functions, but I never talk about like the fermionic ones. But I actually gave you that an example, right? Like a fermionic Green's function, for example, the MFD again. If you want to calculate the fermionic Green's function, you know that like it is given as an anti-commutator, because if you use the variational notation, the functional derivative notation, the signal that I need to hit it with is actually a Grassmann variable, which I cannot realize in a quantum computer because that is not a real number. So this actually poses a challenge. Like, how would you do this with our method without actually just like just trying to use a Grassmann variable or like just something like an ancillary qubit? So we've actually proposed two different ways. One of them is auxiliary operator, and the other is post-selection. I'll be able to talk about auxiliary operator, but I'll skip post-selection for this talk. So auxiliary operator method just puts an auxiliary operator that we call P into the system. That basically satisfy three things. And I'm just going to show you that like this commutator will become this anti-commutator if those three things are satisfied. So you can basically work out this this commutator equal to this. This is basically a trivial calculation. And if you basically assume that this P and B of T prime anti-commutes, that term vanishes, and you end up having something that looks pretty much like something that I have in between these size zero states. That looks like a commutator at the end. So one other thing that I would like is that P hitting this state just better be just generate a number and no other additional operator. So this is another assumption that my ground state, like the size zero state, better be just an eigenvalue of this P operator, so that it just goes out. And the last thing that I want to assume is basically the time evolution of P should be constant. Like P should not evolve. P should be a constant of time, so that I can replace this P with P of T. So once I assume all of that, the Green's function that I calculate turns out to be this. And then I can basically transform an anti-commutator to a commutator. And I always show that for a commutator Green's function, a commutator response function, I can use my method. So that's kind of like an aha moment for us, that we can actually transform these anti-commutators to commutators, and we can measure Green's functions. Well, I'm not going to spend a lot of time for this, but you might be considering like, okay, all these conditions for this P, they're nice, but can we find the P for the systems that we care about? If you're caring about fermion Green's functions where A and B are creation and annihilation operators, you can choose your P to be particle parity operator, which is tensor products of Z matrices for all qubits. And just believe me, it satisfies all of these if your Hamiltonian conserves the particle parity, like it includes superconducting or particle number conserving Hamiltonians. Hubbard model falls on this, superconducting materials falls on this, quantum chemistry models, like for every molecule basically falls on this. So this is a huge set of Hamiltonians that you can actually calculate the Green's function for with this operator. This I'm just going to skip. You just should know that there's another method that we have. Just check our paper. Because I have 3 minutes left. Now I'm just going to show you our results for SSH model that you can find in many condensed matter systems. You can actually implement it. And we show both bosonic correlation function and fermionic correlation function calculations on this. For one, we calculate polarizability. For the other, we calculate single particle Green's function. And we use SSH model is a pre-fermionic model, as you can see. We use our compression algorithm for the time evolution part. We added a little bit more simplification. As you can see, it's not a triangle anymore. we lose these circuits here. I can talk about it later. But this is the circuit that we ran in the hardware and in the simulators. Okay. For polarizability, this is what we get. Basically, we wiggle the potential on the given site and measure the particle density on all other sites. And eventually we get the polarizability that we would like to obtain. This is the familiar structure that you would see. And on the right-hand side, I basically show you the power of frequency selectivity. As you can see, the amplitude is kind of increased. That is something that you would like in a quantum computer because smaller amplitude is more inclined to be buried under the noise. And you basically get rid of all the other frequencies that you don't care about. And these are the single particle Green's function results. This is a noisy simulator result. Here, I just use it to compare to the Hadamard test method. Just look at these two. I was going to talk about this, but I don't have time. If you do momentum selective linear response method as we did, compared to Hadamard test, as you can see, like you can get this cosine band pretty good. Compared to Hadamard test, you actually have a lot of like inference from the other frequencies because every time you change this, you change the CNOT structure, it changes the noise model, and once you do the Fourier transformation, it actually mixes everything up. So the basically our momentum selective method works better. And these are the actual hardware results. We have only used post-selection methods for this. Basically, we counted the number of particles, and we did not use any error mitigation for these results. But what you're seeing all is run in IBM Auckland for A-site SSH model with the circuit that I have shown you, with in total 14 CNOTs. And this is like the gapless with gap 0.4 and gap 0.8 simulations with momentum definite hits. And these are delta equals 0.8 with the post-selection method that I did not talk about, but it also is capable of calculating the single particle Green's function. One thing that you can note is like it goes really good, but it looks like it works bad here. This is simply because we couldn't run everything in the same within the same hour, and the tuning of the machine changes. Like they basically tune it every once in a while, and sometimes like this machine is like an analog system. Sometimes it needs tuning, and this was a bad day for the machine, basically. I would say it's like it was having a headache. So in conclusion, our method is ancilla free. You don't need to append another thing, another qubit. It is more natural. You hit and measure. Eventually, you can do it in momentum and frequency selectivity. Like you can do it in any basis that you want, momentum, position, or frequency or time. You can measure both bosonic and fermionic correlators, and it is basically more robust compared to the existing methods. And I would like to thank all my colleagues for their help, and thanks for listening.
All right, so I think we should open for questions, but you actually dodged the question that someone asked about Lie algebras, and you never actually got to that.
Oh, so
boundary condition.
that's okay.
So you can now do the things that you missed.
Yes, thanks for reminding. Actually, that's good. There are Lie brackets for other reason, but like the thing that you see here is like, for example, I wish I had that in the slides. Sorry. So imagine like if you see this XX and YY, right? So just keep them in mind, and I'm just going to go back to here. So what happens is like if this I+1 is an XX and this I is just a YY, what happens is like you can basically show that this relation is just a like Euler angles, basically. So that XX and YY turns out to be generating, once they take the commutation of them, it generates one additional element, that's a third element. And once you take the commutations of those, they just like generate all three of each other, that's it. So that actually generates SU2. And for SU2, you know that like a generic rotation can be written as a rotation around X, rotation around Z, and a rotation around X, right? So but X is not a special direction. You can actually just like choose Z, then X, and then Z, right? So that is precisely what you're seeing there. So you can say that I can rotate around X, then Z and X, or I could have chosen Z, X, Z. So we actually like use that the algebraic relation of Euler angles, for example. So that's why we call this algebraic compression. So these things form a group, therefore Lie group, because they're parameterized, and therefore there's a Lie algebra, and there's an interaction of different Lie algebras with different indices. So it's like a very interesting structure of Lie algebras that you see here, in a way. Okay. Good.
Thank you. And then boundary conditions.
Boundary conditions, yeah, I don't have it in the slides, but it is in this paper. I'm just going to go back to the introduction. Like that is a little bit different here. So check this archive link if you are wondering that, because boundary conditions in spin models and fermion models are two very different things, right? If you have a fermion hopping from one end to the other end, you will have a Z string in between. So it is doable with everything that I've shown you here. So for fermions, you can choose any boundary conditions whatsoever. But if you are trying to do it for a spin model, then that is actually just like the parity operator, like the particle parity operator that I've shown you times a fermion hopping. So it all transforms into a controlled fermion evolution that we actually like show in this paper, but I didn't add it because of time constraints, basically. So we can compress the fermion evolution in a controlled manner as well. What I mean by controlled manner is like if you have an ancilla and say that when ancilla is 0, you want certain free fermionic evolution. And if ancilla is 1, you want another certain fermionic evolution. We can actually compare, like compress them into a fixed step circuit as well. And there is a local way to do that as well. So if any of you would like to talk about it, like I'm glad to just advertise my work. But yeah, like otherwise, like if you want to just go not talk about it, you can just like check this archive.
And then
So the additional cubic functions like the boundary condition.
In a way, yeah, because like if you have a TFXY boundary term, it's like XIIIX.
Yeah.
That is not a free fermion hopping. If it was YZZZY, then it would be a free fermion hopping. So what happens is this is like a parity operator times fermion hopping. So it's like if your parity is 1, then you apply a certain boundary condition, periodic boundary condition of fermions. If your parity is -1, it turns into like a pi phase boundary condition for fermions, the anti-periodic. Yes, exactly. So that's why you need to keep track of the parity, and that turns into control. Yes. There are other merits of doing the controlled evolution, such as you can measure topological phases for free fermions and everything. But yeah.
Cool. Any other questions?
Yes, please.
It's a very naive question. So is it fair to say that your algebraic compression algorithm actually doesn't depend on a specific realization of your quantum state? So if even I have a classical realization, for example, an MPS state, I can still use this compression algorithm and it will give me a speed up if I want to do time revolution.
Exactly. Yeah. So basically, just as you said, it doesn't depend on the initial state. So like you can generate the circuit, like you can actually generate the time evolution matrix and implement it in the classical computer easily. But since it doesn't depend on the initial circuit, like the initial state, if the initial state that you want to evolve cannot be realized in a classical computer, then yes, definitely, like this will give you the quantum advantage on that. So you can get a very interesting state and time evolve it under free fermions and obtain really good results. Thanks for the comment.
Cool. Any last questions? Okay, let's thank Efekan one more time.
Thank you very much.
We'll be around on Monday if anyone wants to.
you know the 1D